All right, we're live. Let me make sure it's working on YouTube over here. Oh yeah. There we go. Perfect. And I can see the chat in the YouTube comments also. So if anybody has questions as I'm talking, please do post them in the chat, and then yeah.
There's a chat. How do I get to the chat? I'm sorry, I'm stupid.
Oh, it's on YouTube. You're good. You can actually just ask me here on the chat. So you're on the call.
Oh, on YouTube. Sorry, I'll get to the
Pause.
chat. I'm just curious what people say. Yeah, I'll get to the chat too on YouTube. Okay, gotcha. Thank you.
Gotcha. All right, cool. Yes, welcome. Thank you all for joining me. And this will be a brief tech talk, probably, hopefully an hour, max two, about Quantumroot. I'd like to go over a lot of the high level stuff, but then also I'm going to show some of the low level, just contract details, constructions that are useful today, and then how the contracts in the demo use some of the chips proposed for 2026. So I'll give a very high level overview of Quantumroot now, and I've got my presentation here. So Quantumroot first is a contract system. The demo I'll show today is written in Cash Assembly 2026 in the hopes that the chips proposed for 2026 would be approved. But I'll also note that the techniques here are all currently easy to down level and do today on Bitcoin Cash. I do them in a kind of future hopeful version of Bitcoin Cash VM bytecode because it gives us a good sense of what the optimal transaction sizes will look like. So I can show you when we look at loops. I can you'll see that you can unroll them. When we look at functions, you'll see you can also run them in sidecar inputs. And the properties of the system are the same between 2025 and 2026. It's just that the transactions are quite a bit larger. And in the blog post I mentioned, it's between 10 and 100x, and it kind of depends on how you slice it. And anytime I make a slight optimization to this implementation, it changes those numbers quite a bit because, again, this one's quite a bit smaller than what it would be if you copy and paste everything lots. So first, I want to start with, here, I do have a little slide. I had just a very high level overview here. This is a really interesting problem. Post-quantum vaults are a very interesting problem for contract development because post-quantum signatures are huge. They're much larger than what we do today, and there's also a distinct possibility that we will never get quantum computers. And so there's this tension between being ready and then making sure that we don't want to do anything to the consensus layer of a cryptocurrency that is ultimately going to be technical debt if quantum computers like this never arrive. So it's an interesting engineering challenge to get to something that is widely useful for a wide variety of contracts, be able to handle the quantum uncertainty without necessarily committing the network to technical debt. And I'm excited to note that Bitcoin Cash is already well past being able to do that today in 2025 with the May 2025 upgrade that activated May 15th. Bitcoin Cash is already very capable of entirely secure quantum ready contract systems. And that is quantum ready, not quantum resistant. So these contract systems and the stuff I'll show today are ready for a future where everybody has a quantum computer in their pocket. These are Category 5 quantum secure systems. They are considered safe for at least a few decades. and certainly if quantum computers never arrive. So with that, all that kind of background, I won't try to convince you whether I don't have any novel information for you on whether or not quantum computers will exist. And if you haven't looked at this topic in a while, I do encourage you to look at some of the research papers and very optimistic statements being put out by very large companies that are investing now quite large sums of money in build outs for quantum computers. So there has been a little bit of a vibe shift in the industry, in that the threat of quantum computing is taken quite a bit more seriously, and probably I think average timelines have shifted forward between 5 and 10 years, depending on where you look at which expert estimates you're looking at. So if you haven't looked at this question since 2023 or so, you may be operating on quite a bit older information now. So take a look. Yes, I posted this tweet right before I posted the Quantumroot design, because I was curious what. Here, my video is shifting around. Let me just fix that. Let's see. All right, we're good. Yes, so I posted this because I wanted to get a kind of set the stage based on, if you look around the cryptocurrency world right now, most cryptocurrencies are looking at how to do quantum signatures, how to deal with basically the size of quantum signatures. And Bitcoin Cash is really uniquely capable in this area. Obviously, data is no problem, but also the UTXO model and our then relatively generous VM limits allow us to do a lot more than other cryptocurrencies are able to do. One example is that the Solana compute limits are a little bit too low to have a quantum vault of this strength. There is a demo on Solana, but it's not a Category 5 system. And this is the most boring quantum vault you can get. It is a Category 5 SHA-256 hashing, hash-based signature system only. So good for decades, and does model just how well ahead we are based on the architecture, based on the UTXO model and our existing limits. So yes, here is the here's a quick chart that was produced by Chainco Labs, a BTC company that has posted some stuff about this recently. Just to give you a sense of some of those signature sizes, and you'll see that everything is in the thousands for the most part. The ones that are not in the thousands at the top there are elliptic curve, are based on elliptic curve cryptography, which is quantum vulnerable. So when you get to Lamport, you see that things get quite a bit larger. We can talk about the system that Quantumroot implements is actually on this page, but it's inside of the one that's under Lamport. We do not implement XMSS because we don't need to, and I'll talk a little bit more about that later. But Quantumroot demonstrates how we can use the advantages of the UTXO model and get really great privacy and great efficiency. And then as soon as we switch to a quantum scheme, we can get the same kind of efficiency you would expect if it was an account-based model, but without having to revert to a low compute limit situation. So anyways, I wanted to show some of those numbers. The actual quantum signature in the entire overhead of quantum signatures and contract system for Quantumroot is around 2.6 kilobytes. So just barely over the signature size, and that includes the code and the serialized byte code and the overhead of transaction details. That's hashes and everything like that. So we're very, very close to what is thought to be optimal here on this page. So just for fun, I posted a poll, and you'll see that I have each of the options are less than something per UTXO, and specifically it's for an average transaction. An average transaction has 2 UTXOs, so you divide 2.6 kilobytes by 2, and that's a pretty good estimate of what a user's typical wallet will end up spending per time they've received money in their wallet. So it's a really clear apples to apples comparison with an account-based system that is also implementing quantum signatures. So I posted this for fun. I also, the other quote there is Zuko of Zcash, who is a co-author on the original Sphinx paper, is responded to the poll with some kind of explanation for why it's a good idea to go with a hash-based signature system. Yes, certainly, and for the reasons I mentioned earlier, also that you want to minimize additional security surface area, and we already depend on SHA-256. We're pretty confident it works, obviously, because our consensus relies on SHA-256, and that is the only scheme required in the Quantumroot construction. And then going a little further, implementing any other quantum signature system necessarily bears some actual cryptographic risk. Here, I'll go back. That in my post here, I mentioned that the SIDH or SIKE, as it was renamed, super singular isogeny Diffie-Hellman key exchange, was believed secure for 10 years before being crushingly broken in 2022 by a classical computer. So that was not a signature system. That was the key exchange protocol, but discoveries like that cause us to reconsider whether it's a good idea to deploy novel schemes specifically for a quantum threat that has not yet appeared. So I want to point out again that a big part of the challenge of this problem in general is finding ways to not burden Bitcoin Cash in the long term with any changes for the purpose of quantum cryptography. Instead, we want to use the contract system to the maximum extent and make sure the contract system is capable enough to work as if we had done a network upgrade, but allow people to do it permissionlessly. So that's what this contract system does. My answer to this poll is the top one, less than 2 kilobytes, because it's 1.3 kilobytes. And I thought the poll would be fun to post because much of the wider, at least in the UTXO space, the lowest estimates I had seen until I posted the poll were about 4 kilobytes. So I was curious if anybody would respond with how to get it lower, basically. So here's I'm going to leave it at this for a moment. At a very high level, actually I'll switch it over here so it's maybe a teeny bit less distracting and just talk. At a very high level, the Quantumroot setup. First, it's a contract-based alternative to Taproot. If you're familiar with that system for BTC, that proposal for UTXO currencies, the wallet you're using can have multiple spending paths where you can have a single signature that spends the money, or you can optionally fall back to a 2 of 2 system, or optionally fall back to something else. And each of those spending paths is committed to a Merkle tree. You hash the spending path and hash the nodes together until you get a Merkle root, and you send your money to the Merkle root, basically. And that's how Taproot works, and it's a network side upgrade. It's an upgrade to the base network. It's quite a bit of complexity and lots of very kind of use case specific details. It's very tuned to shave every last byte from specifically how BTC works, and with the assumption that quantum computers kind of will never exist. So I thought it would be fun to demonstrate what it looks like in the contract in a purely contract approach to build a quantum safe equivalent and then push it as far as Bitcoin Cash currently lets you push it. So the from a high level perspective on BTC, for example, every input must have its signature content. Every UTXO, in order to spend every UTXO, you must put the signature content to spend that UTXO right in that input in the transaction. And so even if you have a vault that has hundreds of UTXOs that you want to spend, quantum signatures in that model end up costing a huge overhead of the money in your wallet. If you want to sweep 10 UTXOs with quantum signatures, you are paying, if it's 4 kilobytes, if you're using a stateless scheme like was proposed by some of the BTC firms, you're paying 10 to 20 times what you're paying in fees today on BTC, and those fees are already high, depending on network congestion. So Bitcoin Cash already, just with introspection, allows us to design our systems to support cross-input signature aggregation in a completely classical way. There's no magic crypto, no elliptic curve cryptography, very little to understand. It's literally just looking to see if there's a signature that matches what it needs in another input. Extremely straightforward to review. And then also, because we have cash tokens, we can also do another kind of aggregation where we aggregate across addresses. So if you have already signed for a particular UTXO, if you've signed for a particular address, that signature should be good for multiple UTXOs in this system. Obviously, it's not actually, it's to highlight why it's important to do these things at the contract level. That's not an assumption you can make about all contracts. It's only an assumption you can make about your own wallet, that if you can sign for one UTXO, then being able to sign for another equivalent UTXO would be the same, would also allow you to spend the second one. So we demonstrate cross input aggregation and also cross address aggregation. And the cross address aggregation uses cash tokens to identify whether or not you have the authority to move funds in this vault. So first, we prove that you, if you're doing, I'll talk more about it actually as we get to it. There are two kinds of addresses in the vault that we'll talk about. One is the quantum lock address, and the other is the typical receive address. And as we get there, it's important to note that from a user's perspective, the only addresses that they'll show anybody are the receiving addresses, that their wallet shows the same thing as you have a single signature receive address today. And the quantum stuff is entirely internal to the vault and not leaked until Q Day. It's not even possible to associate, by design, it's not possible to associate your UTXOs together by their shared cash token delegation. So we'll get to all of that. Before I continue more, does anybody have any questions about anything I've said on the quantum stuff? Yes, Richard?
Yeah, so just to set the stage a bit for those of us who are less advanced in our knowledge of the stuff, the questions I would like to understand is why are quantum ready signatures so much bigger? What is, if you could give a high level over, what is a quantum ready scheme? What is a stateless scheme? What is a hash based scheme? I don't know if you could talk a little bit about that. I don't want to, I don't know how much of this is kind of background information that should be considered pre-reading versus how much we want to cover off on this call. But that's the one bit. And then the other bit was just about, okay, Quantumroot is ultra efficient post-quantum vault. So there's kind of three things there, right? And then a lot of the stuff is to do with the efficiency. So you're trying to get the number of bytes down.
Yep.
And then there's also the concept of a vault. So, what is a vault? And the first thing that comes to my mind is a hierarchical deterministic wallet, because that has this concept of, having multiple addresses where you can store funds. So I'm curious if there's any analogy there, or if this is something completely different.
Yes.
I know that HDWs, you've got a bunch of signatures, a bunch of addresses, each with its own public key and private key and signature. So I think there's a reason why you're calling it a vault and not a hierarchical wallet. So I'm curious about what counts as a vault. And if we just ignore ultra efficient, what is what does post quantum look like? How does post quantum work in a completely inefficient way?
Yeah, thank you very much. I'll go last in, first out. The HD question, the contract we'll look at is equivalent to an HD wallet. It is just a way of using a BIP32 key to derive all of this stuff. And actually the signing algorithm is implemented also in cache assembly, because it's easier to feed it to a new wallet than having the wallet implement the signing algorithm in JavaScript or something like that. So it means that we can actually carefully review and verify both the signing and the verification in the template system. And if your wallet supports the template system, then you can just import Quantumroot and it will work. And then so on the back end, the reason to differentiate between vault and HD wallet is that I use HD wallet specifically to describe BIP32 hierarchical deterministic wallets. And those are used inside the vault specifically, that it uses an HD wallet correctly, and it's encoded in the template to use it correctly in a safe way, where it's using the output of hashes that are results of different key paths that are hardened in the HD vault. So I know that there are a lot of terms there, but it is using an existing HD key correctly, and it is perfectly possible to add a Quantumroot path to your existing HD wallet, and it would just work if you have a sufficiently capable wallet. Where sufficiently capable wallet means that it can read cache assembly and run the Bitcoin Cash VM on the cache assembly with two additional insertion syntax things that cache assembly provides, the push wrapping and the internal evaluations. So that's by design, that it all works that way. The underlying goal being that the Cash VM, the virtual machine that Bitcoin Cash uses, is a very easy programming environment to standardize for Bitcoin Cash wallets. There are lots of good implementations, and it's maybe the only standard we can definitely agree on without having to talk about it at all, because it's live on chain. So quite literally, we're using Cash VM inside the wallet to actually do the signing and the verification that you did the signing right before you send the transaction. Okay. And also the tests are implemented in cache assembly. And then externally, I can show you later, but there's a property-based fuzzing suite implemented in TypeScript that is using those tests. So especially the quantum stuff is actually very well tested. The stuff that I would like to get the most review on are some of the high-level things like the cross input and cross address aggregation strategies, and also privacy questions. I've tried to take a lot of concern to make sure that the privacy here is as good as a single signature pay to public key wallet, with the only exception being that if you're the only person in the world using Quantumroot so far, then people will notice. People will know whose transactions are yours once you spend one. But Quantumroot is designed to be extremely general, so that a lot of other contract systems can use the exact same sort of wrapper code on the outside. It doesn't become a part of Bitcoin Cash consensus, but from a anonymity set perspective, it should be better than anything else we have other than single sig P2PKH. And possibly, I'd have to look at the numbers today, maybe even better than if your wallet does something unique with lock times and or Schnorr signatures right now. I'd have to look at what the current ecosystem looks like, but there are lots of ways your wallet can leak in operational security information. This is designed to be really well used essentially with cash fusion between your pre-quantum spends, as you would in a reasonably secure, reasonably private single sig wallet today. And then there's a clear place for how we get to use these vaults and have great multi-signature quantum security, quantum multi-signature security in the long run, without having to move your funds. Your funds are safe at rest now for good, if you moved into a contract system like this. But getting there today, sorry, I lost my train of thought on that one. But getting there today,
I can jump in with another question if it helps. So that makes sense, but again, I'm so far from multi-signature. Like I cannot even process anything to do with multi-signature right now. What I'm curious about is if we were to try and do, so for example, a hierarchical deterministic wallet creates pay-to-pub key hash. You could use that to create pay-to-pub key hash addresses and signatures. If we wanted to do that in a quantum secure way, what would that look like? And I think it would look like something very inefficient, and Quantumroot solves that inefficiency.
Yes. Yeah. Thank you. Thank you for the question. If we were trying to talk about what a native upgrade to Bitcoin Cash would look like to switch P2PKH to a quantum safe scheme, again, we would want to do that when we have a good sense that we're really going to get quantum computers. We don't want to saddle the network with a lot more technical debt. But there are zero knowledge proof systems potentially for upgrading single sig P2PKH, which can't be used for Taproot. And it's there are actually some partially truthful statements about Taproot being upgradable to be quantum safe, but they are, actually here, I'll just switch over. I put this in the blog post so that we can I can say very definitively, and I was quite clear in the blog post that that is marketing. There is no way to actually upgrade Taproot without confiscating some people's money or making them move to a new address format entirely. You'll see lots of stuff about like all we need to do is disable the key path, but that would definitely steal people's money. There are zero knowledge proof schemes where you use BIP32, but not everybody's using BIP32. So if anybody's not, you've stolen their money, et cetera, et cetera. So I've seen a lot of waffling on it. So I wanted to go ahead and just put it in the blog post that no, Taproot cannot be upgraded to be quantum secure. And kind of no matter how you cut it, you're still in the margins of your solution, implying that you're going to confiscate some people's money or leave Taproot unsecure. So, I mentioned that, you could call it Taproot version 2, but I think the more honest thing is to be clear that Taproot cannot be upgraded. You need to make a new Taproot and ask people to move. And it's notable because it's the, actually today, the scheme that I'll show you, the quantum signing scheme that Quantumroot implements was standardized in the industry. It's a long standard scheme, a very long reviewed scheme. It's from the 30-40 years ago now, I think. But it was standardized in 2019. It was adopted by NIST in 2020 in the standard version that we are using all the way down to the test vectors are exactly the same. And we actually reversed the endianness of a few things in order to match the test vectors. So yeah, theoretically, actually, we could save just a few more bytes by having our own standard. but but it's not a good idea. We should just use the standard. It only saves like 2 or 3 bytes in a few spots with function.
Yeah, I get your point about the about not wanting to make any changes to the consensus layer, and so maybe pay to pub key hash is a bit of a bad example. But I guess my general point is just it would be helpful in terms of understanding it to know what a sort of a singular version of this would look like on a single address before we have to do the mental model for the cross input aggregation and the cross address aggregation and all of that.
Awesome.
So
yes.
just like what is a
Thank you.
What is a stateless scheme? What is a hash-based scheme? What would that look like on a single address, even if it's pay to script hash?
Yes.
If that makes sense.
Thank you. And yes, that's a great direction. I wonder if I can find. I'll leave it here. I probably won't try to describe this. There are great like YouTube videos, etc. But from at a very high level, the signature system we're talking about can be dropped in exactly in place of our current check sig. You can think of it in exactly the same way. It has a public key. The public key is actually a hash of what some post-quantum signature systems would call the real public key, and that's just that when you're doing the validation process is to do some additional hashing to get the signature into the format that you expect to be the public key, hash it, and then check it against the public key that you had on the address. So very, very high level, the address holds a hash of a public key. And the signature is a ton of hashes concatenated together that the contract then iterates on one at a time based on the message it's validating. It has to hash them just the right way to reproduce the public key that they gave you. And then you hash that and check it against the UTXO.
Okay, that's very useful. Thank you.
And I mean, we've almost described, so I'll just explain Lamport signatures really quickly. The 1 minute version. It's actually, I promise, the simplest signature system you will find. It is possible to understand with no math knowledge at all. You have to know what a hash is, and that is all. A Lamport signature is giant because you start with a private key, which is 256 32-byte bits of entropy. And then to produce the public key, you hash each one of those and put them all together. And now you have the public key. So you start with this massive set of secret numbers. You give somebody else a massive set of secret numbers that are the result of hashing each one of those. And that is a Lamport private key and public key. Now to produce a signature, you hash your thing. And then for every bit in your signature, you give them either the private key or the public key bit for that part of your key pair. So now you see it is a one-time use system because you're giving them on average 50% of your private key. And if you tried to sign 2 things with it, they can definitely forge some signatures. They'd have to grind for it for a moment. If you give them a couple signatures with this one-time signature system, they can pretend to be you almost definitively. So that is a Lamport signature system. The signature system we use was developed. I wish I'd checked the years a moment ago. I think this is like 1979 or something. These are old systems. Not old. They are well aged. they're classics. Okay. There it is. That's what I needed. These are classic systems, and they have been barely improved over the years to the point that you'll see cryptocurrencies talking about implementing a Winternitz vault, even though Winternitz produced kind of a standard in '79, and the standards they're using are things that were kind of re-standardized with additional security properties in 2011, and in our case, 2019. This was standardized in an RFC 8554 there, and 2019, and then the NIST adopted it in 2020. So Lamport signatures, you have a giant block of private keys, you produce a giant block of public keys. To get to a Winternet signature, the goal of a Winternet signature is obviously to make all that a lot smaller. The way it works is by using hash chains. So you start with your private key, and instead of having a new secret item for every bit, you try to map multiple bits onto a single secret item by hashing that secret item multiple times. So, imagine we had our line of 256 private key items before, and we got to 256 public key items. That's our private and public key pair. It's like 8 kilobytes and 8 kilobytes for a total of overhead of 16. Or actually, no, I think it's 16 just for the signature. Yeah, so I guess you have to, in the verification, you can hash the verification result, and you get the public key. So you can actually give somebody the hash of the public key initially. And when they do the verification, they will get the sort of uncompressed public key as part of the verification process. So that's how you get it down to 16. I just forgotten. Winternet's, so the Winternet's hash chains, the way you fix up this Lamport scheme to fit more data in each bit is you do a little bit more preparation. Instead of just hashing it once, you make a hash chain. And in our case, we hash it 15 more times so that you have 16 spots. And there are a number of standardized, you can do it up to 256 times. So you have a chain of potential spots you could stop along for each private key element before you get to the most public of public keys, right? And because the chain, if I give you something in the chain, up here in the chain, you can forge anything lower in the chain. So you can make the bit get higher on this side. And so that gives you the intuition for how Winternet solves that. There's a checksum at the end, which are some checksum chains. And if you go down the chain on this side by hashing more as an attacker, the checksum adds together all of the positions downwards on the chain to get a single number, and then you encode it at the end in another chain. And that's a very, very clever solution, because if you try to change anything on this side by hashing something to pretend like you got something that was a higher number over here, you would actually have to subtract some from the checksum on this side. Therefore, you would have to reverse a hash. Done.
Okay.
QED.
That sort of reminds me a little bit of hardened versus unhardened HD wallets in a way.
Yeah, there's and a lot of hashing schemes are obviously the wider computer science world has been looking at Lamport and Winternets as classic systems for decades and decades. So you'll see the echoes of it in all sorts of places. But yeah, there you go. Now you understand quantum features. They are quite simple, and it's because a lot of the math that we would otherwise rely on to be unsolvable in a short amount of time becomes solvable if you have a quantum computer. And so the one thing we're pretty certain now, after many decades of review, is that the best you can do is Grover's algorithm, which is a quantum search in an arbitrary key space, and it makes O of n a problem and O of square root of n. But that's the best it can get, and there's a proof for it. We don't even know if quantum computers are going to exist, and it's always possible that that somebody discovers more about that problem. But from our perspective, from an engineering perspective, we can be pretty certain, reasonably certain, maybe the most certain of anything in this whole discussion category, that hashing is probably safe as long as you use 32-byte hashes.
Okay, so then if I can just ask a follow-up question, could you take Lamport signatures and create and adapt BIP32 to to some system that's sort of quantum ready or quantum secure. Don't know the right terminology.
Yes.
That maybe use pay to script hash, and it would mimic a HD wallet, but it would just be super inefficient because you'd have giant signatures for every UTXO.
Yes. Yeah, and actually, so we could just cut out, or rather, you can use the quantum lock contract as is today. You don't have to use the other pieces. The contract that's in the vault right now doesn't need to be modified at all. You would be able to do it today. Or rather, today you'd have to down level loops and functions, but that's a translation problem. You could, I don't know, maybe in another 6 months or so, large language models will be able to one-shot it for you. They're pretty good at it already, actually, if you feed it the Quantumroot blog post. But the quantum lock address in the system is exactly that. It is a single signature quantum check, and that's all.
Okay.
We'll go into it, actually. It's not quite, actually, now that I say that. It has it does do its own signing serialization, and so you could hard code that if you wanted to. Well, I'll talk about it a little bit more when we get there. But today, probably I'll show you in the code because it'll be a little bit easier to point to stuff. But if you're familiar with what's going on in OpCheck-SIG, you have to first get a digest of the transaction you're inside of, and then you sign that thing. And that is how you stop anybody from modifying your transaction in the mempool before it gets mined into a block. And there are some difficulties if you're a contract system and you didn't have the introspection that Bitcoin Cash has. So I believe Bitcoin Cash is the only Bitcoin that can do this on the contract system by far. But if you didn't have our introspection, you would be stuck relying on hacks to get the signing serialization out of, at best, out of OpCheck-SIG, which itself is quantum vulnerable. So in using it, I don't know, there might, yeah, I believe in using it, you would probably, you'd probably hit some issues where a quantum adversary could sweep your money in the mempool. But yeah, actually, they're probably even just saying that there probably are ways to hack. You can hack around a lot of stuff, and I probably can't hack around that. But it would be gross, and we do it the correct way. Let's see. So
yeah, no, that's useful. So just to that's just useful background, kind of like a high level.
Yeah,
we could do this, but it's not efficient, so we're going to do that because it is way more byte efficient. And that's like the difference, I guess, between just mapping HD wallets onto something quantum secure versus coming up with a so-called vault scheme that allows you to do cross-input aggregation and those things specifically for byte transaction size efficiency.
That's right. Yep.
Okay. Cool.
Yeah.
Thanks for the detour. I'll let you get back on track.
That probably is the direction that I should have put in the keynote, but that's why I asked you guys to hop on so that I'd be in a direction that was most useful to people who are listening. So yes, hopefully that gave people a sense for first how simple it is to do quantum signatures. I promise they're very simple. You'll probably certainly simpler to understand for the lay BCH interested hobbyist, certainly simpler to understand than even elliptic curve signatures, the ones that we have right now. All you need to understand is what a hash is. And you can get a sense for why Lamport signatures work and why they're one-time use. Winternet signatures are a similar deal. They are just making it smaller. And then essentially, earlier you mentioned the difference between stateless and stateful schemes. If you've looked at actually all of these, I think all of these are stateless or they're multi-use schemes at the very least. And I want to note that the scheme that Quantumroot implements saves a ton of bytes because we do use one-time use schemes. which would be unheard of in other UTXO models, but we have cash tokens. So it's very easy for us to prevent people from even sending money to the our quantum locking script. Like even looking on chain, no one will have any idea what your quantum public key, or they won't even have any idea that you have a quantum locking path in your Quantumroot addresses. Presumably they'll assume that you do, but they won't have any way of actually proving it. And you could just have other stuff, and it just happens to be in a quantum safe wrapper. So you can have just a typical elliptic curve single sig, and then fall back to a 2 of 2 elliptic curve vault, and you could wrap that in the Quantumroot kind of wrapper, just like Taproot works. It's just that the wrapper itself is quantum ready. And after Q Day, even if you're using this wrapper and you've been using it for pre-quantum signatures all this time, it will not be possible for a quantum attacker to steal your money if your wallet has some basic hygiene, basically. If you're not reusing addresses after you've spent from them with a elliptic curve key. Yes, hopefully that gives you a sense. Are there any questions about the reason? Let me also say, the way that you make a hash-based, every stateless hash-based scheme is essentially a modification of the Lamport-Winternitz approach. The way they do it is they put the public keys in Merkle trees. And then there's this concept of hypertrees where you start with a Merkle tree that is sort of the root of the Merkle tree is your public key, and then in practice the signature is a proof that you're okay with the Merkle tree that you give them that has public keys in it. You're okay with that tree signing for you, and if you make that tree large enough statistically, then it's safe to sign lots of times because you'll never hit the same leaf twice based on the message. So that's Sphinx. And XMSS and LMOTS is what we have, the Leighton-Macaulay signature scheme, a one-time signature scheme, is a component of that RFC. Where is it? There. There it is. Yeah, RFC 8554. There it is. That has a few time signature scheme, I believe is the other thing standardized in that document. We don't have to use that. All we need is the one-time signature scheme. It would be a critical software fault in your wallet that is not triggerable outside of your wallet for you to accidentally reuse the key twice. And then if people sent you dust even if people sent you dust to the quantum output, or if somehow you did get money there, I threw on an introspection-based spend anyways, just for kicks on that part, just to demonstrate that you can still spend that part with a single signature, as long as you sweep all the UTXOs at the same time. And then, of course, if somebody sends you money to an already used one-time vault that you swept all the funds from already, then it's a little bit like sending money to an anyone can spend address. You can actually just scan the blockchain and see, like, everybody who sent money to op1, you can sweep that too. So if anyone who's sent money to an already burned quantum one-time scheme, which again is not exposed to users by the wallet, if you're just doing it for fun, then the owner of the wallet can definitively spend the funds immediately, and then everybody else in the world will have to do some brute force hashing in order to get a signature that will work to sweep from the mostly anyone can spend address that the dust was sent to. But it's funny, actually, the vault owner can continue to sweep stuff from the addresses at a great advantage to the general public for quite some time. So anyhow, that's like a super detail of what goes on inside the vault. But from a user experience perspective, what is demoed here is specifically what I would propose is the best solution to switch from a P2PKH elliptic curve based single signature wallet. This I would say is the starter vault, and I haven't put it. I put it here. This is the starter vault. This is the quantum ready equivalent of P2PKH. which also is very naturally upgradable, so that you can start somebody off. If this is like what you use for your cold storage and you have a P2P-KH for a kind of daily spending wallet, this is an optimal construction to even be able to do some clever wallet side upgrading of the security model, or key rotation. And we can talk about it in the contracts, but you can very, very cleanly upgrade the fallback paths here, so that if you use this for cold storage, for example, you might have like a 2 of 2 standard path that is kind of your safe cold storage thing that you keep offline, and then you have a fallback that is much more involved, but involves some sort of social recovery thing or a company that can help you with it, and you can hide the details of that fallback pattern. And if you want to upgrade that fallback pattern, you don't have to sweep any UTXOs. You can do that entirely. You don't have to sweep the vault UTXOs. You can do it where the upgrade is trustless by moving just one UTXO, which is its relation to the rest of your vault is obfuscated for privacy reasons. So on chain, there's no way to figure out that this token is associated with these receiving addresses you've already received money to. So I put in the blog post, but again, it's like very highly optimized for kind of savings and business vault use cases where you don't want to be receiving, you might receive the P2P-KH and then run it through Cash Fusion. But then when it comes out and you want it to use a stronger security model, this is a good place to put it for a longer term holding. And this vault is very security conscious as you're using it, so that the moment you have kind of de-anonymized connections between addresses, which is reasonable in a lot of business cases if you want it to be more easily sweepable. Obviously, you can just have one-off usage if you want everything to be completely obfuscated before and after Cash Fusion. But yes, there's a lot of privacy thought that going into specifically how to do this, and I would say this is maybe not a P2P-KH upgrade, but an upgrade specifically for if you're using P2P-KH as a savings wallet right now. This would be a better option that begins as a single signature vault, but can be very cleanly upgraded. The fallback paths can be upgraded without any privacy leaks, and the main spending path, where you don't reveal anything that's inside the Quantumroot stuff, will probably be a little bit more solid. That's your go-to, like one of one if you trust the one device you have, or maybe a 2 of 2 setup if you're using this a little bit more like a checking and savings account. So anyhow, yeah. Did that did that make sense? Are there any questions about that? This is a savings account. It's a quantum safe savings account.
Great. Let's dive in.
Yeah. All right. So I think we've covered a lot of good stuff now. I think I didn't even stop on this. I just put all these kind of screenshots from the blog post in a keynote, so I'd be able to prompt myself. But everybody have a sense for that you have spending conditions that you hash, and then you hash those together, and you get the result, and the result is the Quantumroot. That's pretty clear concepts. Probably for people on the call, you're familiar with Taproot already, or have heard generally of Mast. So that's what we're doing here. It's been possible to do this with Cash tokens since 2023, and you can get quite a bit better efficiency with some of the 2026 chips, but not too fundamentally different. Let me just do it. And then any other questions about, I think I've shown this enough. Yes. So anyhow, Quantumroot's quantum secure Taproot would require at the very least a very large migration. So the starter vault, to get a sense now, and hopefully, actually, it was really, thank you so much for the how this is used intro, Richard, because I would have otherwise dived right in here. there are 2 example transactions in the repo that are where I try to make a really good representative example of what you should expect to see in each side. So at a very high level, there are, again, as you're saying, there are 2 kinds of addresses that I'll show, 2 kinds of locking scripts, which then therefore are addresses. One of the locking scripts is the quantum one, and that's called quantum lock. And then the other one is called receive address. And receive address is the Quantumroot wrapper stuff. It actually doesn't have any quantum stuff in it at all. It's fully general. It's just that it is a Taproot equivalent, which is quantum ready. So those are the 2 addresses. Each of those addresses have some different ways you can spend them. So I'll actually show the contracts in a moment. The 2 examples are a pre-quantum aggregation, just a pre-quantum transaction, a typical transaction you might expect for a business who is using this vault today as sort of a long-term storage setup. They have already dealt with any privacy issues before they send the money to the vault. And then after they withdraw the money from the vault, if they care, they could run it back through a privacy system. But the purpose of this vault is to get a quantum ready savings setup that is where you do your 3 of 3 thing, or where you do your 3 of 3 thing with a fallback to external auditors or something like that. So the pre-quantum aggregation is an example transaction that spends 20 inputs. Input 0 is a Schnorr spend. That is a typical elliptic curve signature that works exactly like today if you use Electron Cash or a number of other wallets that are doing Schnorr signatures now. And then input 1 through 19 are introspection spends. So I'll show that first because that gives you a sense for the magic that's going on with how we're using Bitcoin Cash to the greatest extent possible to, at a really high level, we're using the contract system of Bitcoin Cash to get the best of both worlds between a UTXO model and an account-based model. Account-based systems cannot get back to UTXOs, but it's very trivial for us to get the benefits of accounts whenever we want to. And of course, having a UTXO model means that our VM limits are very generous, and it's possible for us to do things like hash-based quantum signatures permissionlessly right now on chain. So anyhow, I will move now to the code, and I've got it open over here. I'm going to show you the pre-quantum aggregation first, and just give you a sense. First, we'll look at what happens in input 0, where you have a signature, and then I'll show you what happens in all of the other inputs. And then we'll talk about the bypass attempt thing that needs to be addressed and is addressed in the contract. So first, a Schnorr spend. Oh, and I've got it open here. So this is BitAuth IDE. It is an interactive development environment for working with cache assembly. It shows you on the right a live. It's technically an omniscient debugger. That's the classic term for it. It, as you are typing, recompiles and reruns your entire program, and then shows you the full results at each step in the code. And I added for Quantumroot. I finally added a few features like tagging of stack items. So you can tag here. I tag this leaf, and you'll see that's the result if I hover over it. So you can mess around and really see what's going on here. Up top is the unlocking script, and then down here is the locking script. This is what is committed to by the UTXO. There's a few things going on here. I'll show you in a moment here, but just keep in the back of your head that there's a push of -1 here, and I used op1 negate as the opcode. BitAuth IDE lets you write either opcodes, or I could just as easily have written a push of -1, and it will encode the -1 as bytecode, and then wrapped in a push, it will minimize that. and it's precisely the same thing. The contract still validates here. But I put op1 negate because it makes it super clear what the intention is there. And I'll show you later in the contract, but it's something to note. And then schnorr unlock is the leaf and proof information. And we'll see that in a moment. There's some other details here. What's going on down in the receive address? We're doing some stack manipulation that's only possible on BCH. They actually well, I'll skip it. Anyhow, there's some cool stuff here that is not available on other forks of Bitcoin Cash, or Bitcoin rather. But we check the depth of the stack, subtract 1, check if that's non-zero, and then that is how we determine what to do here. And there are then the two paths that can go. There's the receive address, there's a schnorr send path, and then an introspection path. So the schnorr spend is doing a little bit of stack manipulation. It grabs the function that is being revealed now. So first we reveal the function to the contract that should be hashed and appear inside the Merkle root. And this is enough. This is enough to emulate Taproot. Or it goes to here. And then here is an internal evaluation. So if you've not looked at cache assembly before, everything that happens inside these this internal evaluation, the $, left paren and right paren ends it, literally is running cache assembly inside your wallet at compile time. So we use cache assembly to generate cache assembly, which is actually very convenient because it's very easy to create and reverse the things that you're validating anyways in cache assembly. It's a very intuitive way to if you're dealing in bytecode, very intuitive way to template things. So anyways, this I encourage people to go and carefully step through this and get a sense for what's going on. But this is you can see it's not too much. This is to replace in the case of P2PKH, to replace 4 opcodes, we replace it with this. There's 15 or something. Then in the else block, we'll go. So this is first we accept the leaf that is being revealed and checked to make sure that it's what was committed to. So we say, yes, this is one of the contracts that's inside the Quantumroot Merkle tree. Now you can continue. And then if we confirm that, then we just invoke the function we've already set. We've already defined the function earlier in case it works. And if we've confirmed that it's safe, then we just run it. And the material to run it is on the stack, and everything is modular in this template. And BitAuth IDE makes it very easy to work with things in a really modular way. So what's really going on inside that schnorr unlock and receive address token spend is right here. Sorry, receive address token spend and receive address schnorr spend. This is the script. This is the unlock for the script. And there's a, here we go. Here's what's going on. You'll recognize it. There's a signature. There's a public key. There's a check sig. So once you've unwrapped the Taproot, you're back to what you expect to see. So are there any questions about that so far? Yeah, Galen.
Sorry for the dumb question. So
it's not.
If you go back to the previous screen,
by definition, not
with the master locking script.
Yes, here. Let's see. For a schnorr spend, receive.
Yes. So this supports like a whole tree of different scripts that it can verify?
Yes, it does.
Is it-
Yes, it does via indirect recursion. And in fact, it's both the most convenient way to do it today on mainnet and also the most convenient way to do it when we have functions, because we don't have to put all the bytecode for unwrapping a tree in the contract here. Instead, if you want to have another tree, you put that in the contract that you wrapped. And so it's possible for us to do exactly what we did up above. We can do it here again and split it two ways. You wouldn't want to do the introspection part because there's no reason to rather the top level. We can talk about this a little bit more, but the top level Quantumroot introspection part is the only part where you need introspection. So you need about half of the contract that I just showed you for the next levels of the tree. And you still get for free the introspection-based cross input aggregation and whatever else you want in there. But it's
the recursion happens here in the contract. Like there's or is it like you got to do multiple transactions or something?
today,
man.
sorry, yeah, no. Today you would use another input for each time you unwrap the tree. But it can be done atomically in the same transaction. So you have an instant setup transaction, which you have to protect from mempool attackers in a way that's described in the code comments. But if you were going to do this today, you would have what it would look like is you have the Quantumroot spend, and then a few of the other inputs in the transaction are these sort of one-time use introspection-based spend time defined bytes that you execute. And you literally push them at spend time, and if the contract likes them, then it will accept that they can be in the same transaction with it. So the contract is down leveling is its own kind of its own beast, but I described it in the code and also on Bitcoin Cash research. So and I can explain it a little bit more, but yes, it's perfectly possible today to push in to do a setup transaction and then stick the output from the setup transaction directly immediately in one of the inputs for your current transaction and execute it as code and have the current transaction rely on it as executed code. So it looks the same as functionally, it's exactly the same as having the functions chip. It behaves the same. The actual execution is in the atomic transaction. So you can do crazy stuff like put a zero confirmation escrow on the atomic transaction. And the fact that it's atomic can be a functional part of the system. You don't have to do it in previous transactions and set up an intermediate activity. If you ask like a large language model about this, they'll get it wrong because in 2018 and earlier, you had to evolve computations over multiple transactions, and that is not the case for Bitcoin Cash. It's not been the case for a lot of things since 2022, but 2023 like fully removed any of the weird logistics you had to deal with if you wanted to evolve a computation even in a single transaction. So what I'm saying there is that since 2023, we've been totally Turing complete, and you can do anything you want. You just have to break it up, right?
Even with the, let's say, so this code is 2026. It's got functions. It can even like sort of compose code on the fly and define.
That's right.
Function.
In the same.
But even with that, like I'm lost on the notation of what's going on in this IDE. Like how are you verifying like the whole Merkle branch or whatever?
Yes.
Or is it happening like as sidecar inputs in some magical way that I don't understand?
Yes. Sorry. And I answered like a down leveling thing, but that is very, very detailed. What's going on here right now is that the Merkle root only has 2 leaves. So I'm not doing another level of the Merkle tree on each branch.
And this contract, it just happens to have 2 leaves and that's it.
That's right.
Okay.
Root, you are here. And then on the other one, it says you are here.
All right.
So
if you had more leaves, would the verify like that big if statement here in the beginning, the 15 instruction if, would that just be more complicated? You just have like a bunch of conditions for it? Is that how do you express that? How do you express the tree and how do you verify the tree?
Only
Like,
you express the tree.
This is a dumb obvious question. I apologize, but
sorry, no. Thank you for the question. That's a great. I'm sure I've not explained it well enough yet. You you provide that information only in the unlocking bytecode. The locking bytecode looks the same whether or not you have any subtrees in any of the nodes, because when you get the leaf, you just execute it. And now you're in the leaf, and the leaf can have its own subtree, and you can do exactly the same thing in the leaf. And then that one of those leaves can have its own subtree. So in practice, Quantumroot is designed to support unbalanced Merkle trees intentionally, because we want the very top level to have a preferred path. The top level preferred path is the Schnorr spend, today's pre-quantum signatures. By making the top level, by making the Merkle tree unbalanced, where the first leaf is just the spend it leaf with a single signature today with today's signatures, this script that you see open right now, by making it work that way, the contract sweeps are actually 15% smaller than P2PKH, and the crossover for the overhead is at like 8 inputs. So if you sweep for more than 8 inputs, this is more efficient than P2PKH today. Does that?
Yeah, no, that makes sense. I guess
Yeah.
you want an imbalanced tree, because then you prefer, like, you can always take the shorter branch. You don't have to
Yes.
do so many bytes. But
Yes, you can design your branches based on how likely you think each one's going to be.
yeah,
And that's like something you would do if you're the wallet developer building your very carefully designed good UX system. That's like, okay, most of the users are going to use this, but we want the fallbacks to work this way. This vault demonstrates how to make the fallbacks upgradable without sweeping users' keys, without sweeping users' UTXOs from the receive addresses. And it also shows how to have the receive addresses unassociated. So the first leaf is the unassociated one. The second leaf is the token spend.
So then if you were to, like, for some reason want to execute some script that's deep inside the tree, like on the right-hand side over there, and under B, let's say, and that's,
yep.
I guess you provide the Merkle proof kind of, and then the leaf to execute sort of as part of the, I have to look at, this is a dumb question. I have to look at the details of how this mechanics, how it works. But
no, it's not a dumb question. And sorry, I forgot that I put a little, so you could just as easily have done this one, right? So the Quantumroot shows this. Here, this script is just a couple byte, this script is just like 4 opcodes or something, and a push. 3 opcodes and a push, 2 pushes. So and one of them is just a privacy thing. So if anybody's curious about this, go take a look at the code, or we'll talk about it in a moment. But yes, high level, you can design trees of any shape, and this is a very solid design if you are building a vault system where there's 90% of the spends are going to take path A, but then the rest of the spends are going to be B or C. And notably, you can have B also delegate to a token, and then have the token be where you do the actual security, so that you can upgrade your security without moving all your UTXOs again for the vault itself. So this demonstrates a bunch of concepts like that. it's intended to be a really like wide-ranging, here's a bunch of stuff you can do. Does that make sense? Or are there any? And Jerry, did you have a question?
Yeah, just I guess just to follow up on that a little bit. So would something like this allow things like helper functions that aren't necessarily there for like determining how the payments are going to be made, but rather just like kind of like it allows you to make these custom functions so that you can pass that information to whatever next step that you're in?
Yes. So and this gets really esoteric, but yes, it is possible to memoize computations across inputs. You can have one input produce the result of a computation, and then have other inputs look at that result, atomically in the current transaction. And you can do it with code that you only commit to at signing time. And that's definitely possible right now today on mainnet. This does it the less obscure way by using proper functions that you accept and validate correctly and then run. But yes, it's very possible to do that with, you do a setup transaction to define all the code, and then you execute it all in the same atomic transaction. And that means that from the perspective of a contract system, it's exactly the same as if you had the functions chip already. It's exactly the same as this. It's you can down level this contract, and it will have the same properties as the more efficient version that I've written here with 2026 stuff. It's just I'm sorry, and the same properties being that you can, sorry, I almost lost my train of thought. The same properties being that you can then build this system into other UTXO-based systems, because this is at a zero conf level an atomic transaction. And the functions are executed atomically. So you can do stuff like zero confirmation escrows, or build it into a decentralized exchange that relies on the bounty kind of atomic bounties like ZCs. Okay. Did that answer your question, Jerry?
Yeah, more or less. I was more looking at it like adding, like these custom functions, like for example, some of the elliptic curve related math operations, so that instead of putting it on the script level, just custom build one of these functions and then just require that as part of the overall payment setup.
Okay, yeah. I think if I understand correctly, you do have to have the code that gets executed has to be somewhere inside the transaction, no matter what. And so in practice, it needs to be encoded somewhere in the transaction at least once. You can do some clever workarounds to make each invoke today cost about 140 bytes or something. And with the function chip, it would be 2. But you can't like call out to another contract that has the code and have the code not be represented somewhere in this transaction. And that's a useful problem.
Yeah, it'll be all within the same the root setup and whatnot, and just going down whatever leaf path in that same root.
Yeah, okay, sharing functions between leaves.
Yeah.
Okay, yes, certainly possible. Logistically, I think you'll, unless I'm missing something, I think you'll find it won't save any bytes. And it might be a privacy concern to try to associate. Well, no, sorry. What am I thinking? It's within the Quantumroot stuff. Yeah, for sure. And in fact, it'd be a lot more. If you were trying to deploy something that was really practical today, and you didn't want to have latency ever impact user experience or something, you probably would actually do exactly what you're saying. You probably would pre-set up a bunch of executions of the code that you want to run, so that your wallet can just include them like like little coins in the transaction to make it do the execution how you want it to work. Of course, my preference obviously is that we would just support functions, but yes, for sure that's possible. Yeah, and check out the Bitcoin Cash research post I put up yesterday for kind of a detailed description of how you down level like one of the simpler things in Quantumroot. And down level meaning translate it from the bytecode here to something that works today. Okay, sorry about Callan. Did you have another question?
Yeah, so like just forget about down leveling. Let's pretend we got functions now the way you propose them, where you can dynamically, push
Yeah, take it from unlocking bytecode. Yeah.
And then I guess the way you walk down, because I'm kind of dumb, man. Like pretend I don't understand anything. Like for the purposes of exposition, like if you wanted to sort of walk down the Merkle tree to execute some embedded leaf, you just like recursively kind of do the root thing, right? Where you just check Like each script contains more scripts that contain more scripts that eventually get to the leaf or something.
Yeah, it gets way simpler to understand if you have functions. If you have functions,
and if
then,
you don't, let me just cut you off. So
Yeah.
if you don't, then you have to sort of set up sidecar inputs or something. That part I don't understand at all. Like to me, I can only understand it with functions and with this ability to dynamically.
Yeah,
I can't understand the other way of thinking. With
yeah, and it's definitely harder to understand.
Yeah, I just want to make a comment.
Yeah. With functions, it's certainly easier to understand and review, obviously, and that's a major reason why they would be useful. But yes, with functions, it's quite a bit simpler. Just without looking at the code, I probably should have, if I had unlimited time, I would like make a nice diagram instead of trying to show you the code. But really high level, the unlocking bytecode is just layered. The kind of the top thing on the stack when you're finished with the unlocking bytecode is the top level stuff you need to deal with the top level of the Merkle tree, of the Quantumroot Merkle tree. And so in this case, we push some code that is committed to in the Merkle tree, and you hash it and check that it's in there, and then run it. And then you have the next thing on the stack is whatever data you needed to run that script from the Merkle tree. That section in the program, and BitAuth IDE is designed to make it really easy to work with things modularly like this, where and by the way, this is like downstream of how Forth works. Like there's a whole era of languages that were designed to work this way, and defining words in Forth was a way to control complexity of systems like this. So scripts in BitAuth IDE can be referenced from other scripts, and it just drops them in that spot. So what we were looking at here is actually running. I've slowed things down. There we go. What we were looking at here is actually running everything, and it's dropping in the schnorr unlock and the receive address schnorr spend that we were just looking at. It's encoding them properly. This one is actually dropping in another script, hashing it, and pushing it in the unlocking bytecode in the right spot. Yeah, there are. It's probably, I'm going to switch it over here because it's confusing to the point of not being useful to look at the unlocking byte to understand. But yes, you start the first thing that's on the stack when the locking bytecode starts to run is the top verification stuff for the Merkle tree. It checks that, and if it's okay, runs it. And what's inside of that can be the same thing without any of the introspection stuff. And then it's actually quite simple. Then take the next item on the stack, assuming it's a function, take the hash of, duplicate it, define it as a function and get that out of the way, and then hash it and check that that hash is inside of the leaf you just unwrapped. And if it is, you can run it. And that leaf might have the exact same construction yet again. And the number of spending paths you can have balloons out very quickly. So the max you're going to do that's like twice for the vast majority of cases. If you want to have a different balance, you actually can. You can have a Merkle level that has like 5 leaves, and you can have it split to 5 leaves. So like Taproot is extremely, Quantumroot is extremely unopinionated. That's the right word. It's extremely unopinionated in how you will choose to design the frequencies of the paths in your wallet, or how you'll choose to have some paths be upgradable and some not, and what you want the efficiencies to look like. But without fracturing the anonymity set, so that everybody who's using Quantumroot blends together, you can get a very great deal of flexibility. Did I answer your question about how to unwrap?
Yeah. So it sounds like you just you just a recursive like Chinese doll. But it sounds like if you want it to be really efficient, your most common spend paths should just all be leaves, kind of behind the tree, and then your uncommon, right, or something like this.
That's right. Yes.
Because you have to walk down the tree deeper, and so you're just doing more like recursive evaluations when you're doing that.
Yes.
Right? When you get to elite, you're done. So you want your common stuff to be up high. Is that correct, or?
Yes, that's exactly right. Yes, that's exactly right.
I don't know how Taproot works. I mean, do they also optimize this way, or are they just? I guess because they have it built into the consensus. Maybe
it's designed to work with unbalanced trees, but it's on the protocol level, carefully designed to with a rather application specific approach.
So they're biased towards like balanced trees or something in the way they
unbalanced trees. It's but it's it's non-trivial to implement it as an upgrade, and then it's non-trivial to implement it as a wallet. But once you've implemented it, then and figured out a way to encode how you want to ask the wallet to produce them, it's definitely a more application specific kind of brittle approach to solving the problem versus something that's like solving it with generalized contracts that you can import into new wallets. So a major advantage here being that deployment of Taproot took many years even to get basically Taproot wrapped P2PKH into many wallets, and I think there's a good chance that we can use kind of our higher level tooling to make it much easier for wallets to integrate this kind of stuff, where wallets can trust that the template has been well reviewed, or they can perform their own security audit on the template, and then there's no application specific code to be written to make this particular template work. The template itself describes how to make it work, and so the wallet can do exactly what it needs to do. Yes. Yeah, Callan.
One last question. So just to wrap up, so since the thing that's on everybody's mind right now is like the 3 different function chips variants that are basically all derived from your proposal, and 2 of them are mine. And I actually prefer your proposal, but I came up with alternative proposals to address some people's concerns. So if I could just refresh everyone's memory, they have different ways of restricting how you can execute code. It sounds like the one that came from Bitcoin Cash Artist, the executable bit one. It sounds like that's more compatible with the system. Because the one I have is restricting stuff. You can't even run hashing. You can't do anything before you can define a function. Basically, the only thing you can do is like move stuff around in the stack. You can't like hash the way.
It's possible.
Or you can do. Or I guess both of them can do. You could dupe. So you could dupe and then
I need to review really carefully.
Check the hashes later, I guess.
Yeah.
Yeah, I guess both of them. So it sounds like, because you're not like combining scripts or anything with this, right? Or you are somewhere in some other contract. You're not like composing scripts like concatenating data.
Well, actually, what Jerry was asking there would be a use case of combining scripts. Yeah, I maybe I want to avoid digressing on chips too much because I'll get carried away. But I responded on Bitcoin Cash Research, and maybe we can talk more about it there. I think there might be kind of an underlying misunderstanding that there is something you can do with the functions chip that is not already possible today. And I'd like to kind of get
but I don't want to get into that whole can of worms. Just like how to make this easier for people to work with and understand. I don't want any of the chips I propose to have some dumb limitation that, like, if I just change that limitation, you could do something like this easily.
Oh yeah,
sounds like all the limitations that were proposed are compatible with this. So that's all I wanted to get to. Just not aside from the other discussions. Just proposals seem like
on Bitcoin Cash Research I described in detail one that I think it depends.
No problem.
Jerry, did you have a question?
No, it's fine.
Oh, cool. Okay, your hand is up, and I'm just looking to see if there are any questions. If anybody doesn't mind reposting if there are any questions in the chat. I do want to go ahead and show the introspection spend here. So just so you get a sense, because this is what maybe will seem like magic to if you are not looking at the code itself, because and maybe why we've not seen this used much is that it has kind of a circular dependency on itself, and this is just using introspection. This doesn't require any of the chips, but there are two paths. One is the unwrapping path we talked about, and then if the unwrapping, if you only have one item on the stack, then we assume you're not trying to unwrap, and we assume what you're actually providing is an index to look at to see if this transaction is authorized to spend authorized to spend this UTXO. And then we check to see if that UTXO is the same contract as us. And if so, you're good. You've proven you're allowed to spend from this address. You may have it. And that's how we do the introspection base. So it's literally only using introspection on the contracts. There's no token stuff. And that makes stuff really, really, really lightweight. And again, it's 15% lighter weight per UTXO than P2PKH because you're not paying for the extra, for some of the extra overhead. So that's the magic. And the real magic is that we can, the contract takes it as a proof that a sibling spend is a valid leaf spend. That's what we call it, where you've unwrapped the leaf from the Quantumroot and you've proven that this is in the Quantumroot thing and that you've satisfied it. It's returned one, right? So it's a valid input. By definition, if it appears there as a valid spend of itself, then it trusts that it is a leaf spend. And the way that we identify cheaply that it was a leaf spend is that all of the leaf spends, the one place where we put the actual signature, we preface the input bytecode, the unlocking bytecode, with a push of -1, which is a one opcode item, and it's a specific optimization choice because there's only 17 numbers you can push with just one opcode, and this is the one number that's not a valid transaction index. So it means that you don't have to have any wallet-specific code for deciding where you put inputs. No matter what, your wallet will be able to mark this input as a -1, and it won't be an issue that you can't look at index number -1. So anyhow, the fact that there is a -1 in the Schnorr spend is a feature, a critical feature. And this is, I'd appreciate reviews. Make sure I'm not missing anything huge. Anything would be huge actually. And I'll show in a moment a potential bypass, which I believe is probably why we've not seen any contracts, as far as I know, that do this. It's because unless you bang your head on the problem for a while, it's not clear that it's remotely possible. So, and I hope by sharing it with you guys, I might still be totally wrong. So I hope by sharing it with you guys, someone can really review it and tell me I'm not crazy. But if you preface we actually force leaf spends to be prefaced with op1 negate, or maybe I'm not actually. Yeah, I'd have to double check. Doesn't really matter because malleating would cause the script to fail. So we don't. I don't think we check the number now. I'd have to check. But I went through and really tried to optimize stuff and based on what you actually have to check to prevent malleation. So Quantumroot is non-malleable, and I could have made some other trade-offs so that it is malleable in the mempool, and I just didn't want to deal with people being like, that's malleable, so I added 3 extra bytes or something to make it non-malleable. So if that interests you, please let me know if there's another thing that I missed. But yes, the op1 negate being the prefix of the of a leaf spend is how we prove to the top level contract that which is the receiving address of all of your vault, all of your outputs in your vault, and all of your UTXOs in your vault. We prove to them that yes, I have permission to spend from this address, and so if so, you're good. And the address trusts itself, right? So the address trusts that its own signing serialization deep down is okay. It doesn't have some issue that an attacker can spend from one address. If it did, then an attacker would be able to spend from all the addresses. So it's fine if you introspect to just check that there's some proof of an address matching this one. Now there is one. Now we'll go to the bypass attempt, just so you have a sense of one thing that is not immediately obvious, but then seems like a deal breaker, is that you could put both. You could put 2 inputs together in a transaction that use this system and have them look at each other and both decide that the other one has the proof. And that is not possible because of an explicit check. So that is, I described that as a leaf spend bypass attempt, and the transaction specifically fails if you try to put two introspection spends that reference each other and neither is a leaf spend. But that's why you have to do some of the gymnastics in the opening of that Quantumroot spend. So yes, are there questions about that now? Yes, Calvin.
Yeah, I'm a little slow today, man. Like, I don't know, I'm drinking coffee, but it's not working. I think I understand. Just to you tell me if I understood correctly. So a leaf spend always starts with a -1. So, right, and that you take the first branch of the if, right, and then that actually does like real validation of spending. And anomaly,
yes, yeah. So
anomaly spend is an index of some other input, right? Is that correct?
Yes, that's right. The leaf spend has like all the proof, and it can be spent on its own. And so the other ones just point to leaves.
And the other inputs in the transaction are basically spending from the same contract, this code, and they're just providing as proof, like, hey, there's this other input that actually did the real validation in this transaction, right? Is that?
Yes, that's right.
Yeah. Okay.
Yep. And then there's just one.
And then the way you can differentiate them is the -1 versus not -1.
That's right. And it's a flag that we use as proof. And the contract like respects it above all things, that that if it's prefixed with a -1, alert this this will prove to itself that it's already been valid in another input. So we got to make sure this can't exist except for if you're actually, if it's the truth.
Yeah.
Right. So
right, because like people just have to realize that. So this this one input may have validated correctly, but then the final input that's maybe the actual leaf spend may not validate, so then the whole transaction is rejected. So that's fine.
Yep, that's right.
And then the magic of this, I guess, is because we have the introspection of the UTXO bytecode and input bytecode. Because if otherwise you wouldn't be able to embed a hash of a thing into itself.
Yes, that's exactly right.
You don't have to do that. We can rely on consensus layer that can just bring in the actual bytecode, and then you don't have to worry about setting hashes of themselves into themselves. So yeah, it's kind of cool. Yeah, the recursive nature is kind of mind bending, but I think I get it.
Yeah. When you modularize it and really break it out, like each contract here, obviously, like on a video call where I'm just waving my hands, it's a little bit harder to grok it. But each contract here, if you spend 5 minutes, you can look at just that component and I think come to a conclusion that the component you're looking at works the way it's expected to work. And then again, as you zoom out, the language that Satoshi chose is very natural for concatenative programming like this. That's what it's for. So yes, I think I've covered now introspection spends, and hopefully that's a clever contract technique that will will be interesting. I think I'm sure lots of people have explored it before in the abstract, but again, it does on its face look like you need to have a hash referencing its own hash, right? So it's something uniquely possible on Bitcoin Cash right now, since this one, I think, just since 2022, it doesn't require any cash token stuff. Yeah, so I would appreciate deeper reviews, and let me know if especially if you find any optimizations. Also, I've tried to do pretty well with optimization. You also find in the Quantumroot blog post where I added an appendix for recommendations on how to optimize your contracts after working quite a while on it, and it makes large language models quite a bit better at it. So that's a curiosity to give a shot if you're trying to optimize something. So if we understand the Cypherpunk BCH, did you have a question?
Yeah, hey. So I just wanted to mention a little bit about the introspection spend. Hey, am I audible?
Yes, can hear you. Yep.
All right. Yeah. Okay. So especially with the help of the loops, we can easily have introspection spends. I prepared an example and I shared it in the loops chip, where you can basically have just one contract, which is the root contract, and that contract itself will have all the verification that needs to be done for. I use the example of Cauldron. So you just need the root contract that does all the verification for all the contracts that are exactly similar to any Cauldron contract, basically. So now the Cauldron contract itself can just have two entry points, where one is basically the LP provider can just withdraw their own funds. So that has like their own BCH. So they can, provide their signatures later on. And the next path can just be it pointing to the root contracts locking bytecode. That's it. Like this is the only extent of how much it needs to spend in any transaction. So basically what it provides us is we can have tens and hundreds of inputs, but all the logical execution only happens on the root contract. And all the inputs, all the other inputs that are spending within the transaction, they just point to the zero, basically the root contract itself. And it trusts that its own process has already been done in the root contract.
Yep.
I just wanted to give that as an example.
Yeah. That's a very similar thing. And we chatted in Telegram, sorry, I a couple days ago. Double check, make sure that the bypass attempt is that from Quantumroot here, double check that isn't a vulnerability in what you're just describing. It's just something you have to check specifically because it's very easy to accidentally miss it, and and then it's possible to spend your UTXOs by mutually referencing each other and not actually providing the proof. But that's sure. There are several ways to do it, and I think Bitcoin Cash. Bitcoin Cash's VM is quite powerful now. You can get quite a bit of distance in very few bytes, and especially things where you're deduplicating proofs across inputs. You can get quite a bit of distance just out of introspection, and certainly with cash tokens. Some of the things that you expect that you can do, you'll notice when you actually build example transactions and then try to build a transaction on top of it, you'll notice that the proofs start to get larger or something, and you need to break a place where you're using where the proof shows up in the next one. But with cash tokens resolved any case where introspection didn't make this stuff possible. Cash tokens fully did get us to Turing complete. That's hopefully the takeaway here. Okay. Are there any other questions about this stuff before we talk about token spend? And with the token spend is actually super simple. If this stuff made sense. So the token spend is just the other path. You just provide the other side of the Quantumroot and unwrap it. And here's the whole contract. Let me open it up a little bit and you'll see a little better. Don't let the comments scare you. It's 75 lines and there's only 5 lines of code. But I describe in depth why it's important to have a nonce here. This is another place where I just want to highlight that having a generalized system for describing contract systems is extremely useful, because this nonce source is actually a key path. So like from a really high level, if you have a wallet that has hopefully at some point in the not too distant future just like imported some utility functions from libauth, you'll be able to feed it this JSON template and give it also a hardened key path at that moment, where you say, here, give this template this hardened key, and I've marked in my backup that this template had this hardened key, and you can reproduce every behavior of the wallet then from that single function call, basically, where the whole wallet, including how we derive and map key paths and whether or not they should be hardened and exactly what the index it should be, all of that stuff is encoded in the template and it's in a JSON scheme. And the JSON scheme is like several years old now, actually. So obviously I've been working on getting some of these general things working a little bit more smoothly in our contracting system. But the long-term hope is that you can see that nonce source .public key, just because we don't have another way to access the just give me the entropy from that nonce source. Obviously, we're not using it as a key. We're just throwing it in there as the result of a hash that the attacker can't predict. But by dropping it in the contract here and literally pushing it in the contract, we never increase the size of pre-quantum spends. We only increase the size of these token spends. And it's a trade-off. If you were going to use this construction in other contracts, you can choose whether or not you want to add a privacy nonce like this. But the goal here is when you spend pre-quantum quantum root, when you spend with pre-quantum leaves in the quantum, when you spend from leaf A, you are revealing the hash of leaf B. And if the hash is consistent, and you revealed it in lots of different places, if it's consistent across multiple UTXOs, now you've associated multiple previous UTXO activity together. And so it matters what is revealed by the hash when you unwrap. And here we include some entropy, and it's also resistant to quantum attackers because it's 32 bytes, to ensure that your pre-quantum spends cannot be associated together unless you specifically associate those addresses deliberately in a single transaction. And it's possible to sweep only a part of your vault and hide the fact that half of the vault has not been swept or something. So that is a key privacy concern that is addressed, and there's more description there. But yes, privacy nonces are a important idea if you're doing token spends. But then you'll see the rest of the contract is quite simple. You check if the category that you expected is there. You check if the provided input has that category, and if so, they're good to go. They can have the money. And in practice, that just is delegating the validation then to that contract. And now you're trusting a token category with only containing the code that your vault expects. And obviously that's the case because your vault created it. And then the token category is where you stick your super fallback stuff. That's where you stick the quantum fallback. That's where you stick the social recovery and the company you're using or whatever. And you can avoid moving any of your UTXOs from your receive addresses, right? while upgrading the actual code that gets checked to see whether or not you can sweep. The actual code that gets checked is in that UTXO, and you can move that UTXO on chain, so you have a trustless way. And there's also a way to upgrade just in the wallet depending on the purpose. And I'll show that in a moment, actually, because it's useful to talk about. So is that clear? Is there any question about just delegating to a cash token as saying that this cash token is just the super admin key for the whole vault? And if you reveal a leaf, in this case, you're revealing a leaf that reveals that admin key exists, and only at that moment can people associate the UTXO with the admin key that's been on chain, right? So you put it on chain, and you can even move it around so that you can upgrade your security, but only at the moment you actually end up using it can anybody ever tell that some past address was associated with it. And there's all the possibility in the world that most of your past addresses will never be associated with it, because you'll never have revealed the pre-image, which is the privacy nodes. So is that any questions on that, or just looking at the I see it. Could you just grind the key paths if necessary? Presumably for yes, for if you are asking, like, I gave, if from a wallet's perspective, I gave all the templates. I gave each template a specific hardened address. I'd go a step further and actually say that it's quite easy to hash the template, because presumably if you're going to use the template, you can check its hash and use the hash as the way that you derive the key path. And then you never have to grind. You can just check if you have any money there. And you can check for an arbitrary number of templates. So you can just have like a whole template library and try to sweep from the whole library, given a private key, and it can just check and see if any of the money's there. And if you have a trusted way to look at the blockchain, if you're running a full node locally, or that's pretty much it. You need to at least have the UTXO set. Probably running a full node locally is the best way to do it, because you need to be able to see stuff that is early on in the derivation path. So in practice, your super recovery machine probably should be on at least have historical blockchain access also. But yeah, to answer, yes, you don't even have to grind the key paths. You can standardize a strategy for template library. Perfect. Oh yeah, there we go. I don't see any other questions right away. Okay, so we should wrap up soon. I don't want to make the video too much longer. Does anybody have any questions about stuff I've shown so far? Great. I'm going to show one other thing that I think is maybe immediately interesting. Where is it? There we go. So serializing the transaction. This is what's actually going on. We're using introspection to serialize the transaction. Here we have essentially constructed our own SIG-hash all SIG-hash UTXOs signing serialization digest. And that is what the quantum signature is signing over. Notably, and this is like just zooming out quite a bit. The quantum. Oh, I wonder if. No, that's not gonna be helpful. You can see the post quantum aggregation example has a couple different ways to spend each kind of thing. But I think you've already gotten the idea. So I'll just describe what the quantum signature is actually signing in this implementation. And you wouldn't necessarily have to do this. You could also have it just sign a fixed signing serialization where you loop through all the inputs and outputs. This is a place actually where loops and or functions makes things a lot simpler. you need to, if you want to be able to have to cover the transaction in different ways, it's very useful to be able to add together essentially a hash of each input and output to make sure that somebody doesn't change your transaction in the mempool and change the amounts or change where it's going, right? So you need your signature to cover the whole transaction so that if an attacker tries to change anything about it, the signature is not valid and their version of the transaction doesn't get mined, right? So another kind of important thing to consider is if over the long term with a vault like this, if you want to avoid moving it for a while, if there were another upgrade in the future which was similar to cash tokens and then it added like a new primitive that's attached to the outputs, that's theoretically possible. And so if that were to happen, there would be probably new introspection opcodes that come with it. And if you had locked your money to a template that had specific introspection opcodes hard-coded, then you would just be hosed if somebody sent you, that new kind of cash token or whatever that has its own sig hash limits or is somehow not perfectly backwards compatible with the existing token coverage, right? So this sig hash algorithm, and I'm sorry, I'm still up here, but I'll just, it checks over the inputs, it loops over. As an aside, looping backwards is a little bit more efficient. You can search for what I've written about that if you want in here. And then we loop over the outputs and do the same thing. We get output bytecode value, token category, token amount, token commitment, right? So we're committing to everything. And we end up with a serialization hash. And this is, by the way, an internal script. This script is used elsewhere. So we have up here a setup, and here's just a test written again in cache assembly to make sure that it worked. But at a super high level, the quantum signatures sign both a digest and the code that produces the expected digest. And there's actually like two different purposes covered by the signature. And one, you're proving to the network that you're allowed to spend this UTXO. The signature covers that you're allowed to spend this UTXO because you provided a signature for the UTXO. So signing anything would prove that you're allowed to move it. The next step is ensuring that your transaction cannot be changed such that your proof can be used for somebody else to take your money now that it's in the mempool. And that's what is happening here. We sign the script that defines how you cover the transaction. And then we also execute the script and concatenate that and sign that too. And that whole block is what is signed in the quantum signed message. And so you, in practice, are pushing in bytecode, in the unlocking bytecode, you're pushing the quantum signed message. To answer your question earlier, Callan, there's plausibly places you could reduce this in size if you did it with metaprogramming, but I chose to make it as clear as possible. So that's one place you could do some metaprogramming. But I do want to note that you are pushing unlocking bytecode and you're pushing the bytecode that you want to execute in the unlocking bytecode as part of how you cover the transaction, as like a core part of being able to build the quantum signing, a quantum equivalent to object sig. Does that make sense? I know that's like a little inception.
Yeah, that makes sense.
Yeah, cool. Okay, and then the only other things in the contract, if you're curious, are a complete and thorough implementation of RFC 8554 with all the test vectors, and the test suite in the GitHub repo actually runs them against property-based fuzzing. So it runs it a few hundred different ways for various cases, and some of the smaller components get run thousands of times each time. But yes, anyhow, the test suite is a fuzzing style, property-based fuzzing style test suite right now. I next plan to, let's see, I'll just bring it back over here. Yeah, so I next plan to continue on security review, making sure I have not missed any other kinds of bypasses like the one I described. I think that that bypass is something that if you've experimented with stuff like this, make sure your contract isn't vulnerable to it, because it's like really easy to just like not notice or forget. And it's something that that a linter or auditing software should be able to do automatically in the not so distant future. But again, getting our contract system to that level of capability is first. Is there any further questions on anything we've talked about before I close the live stream on this? And I'm going to look at the web too. I saw a notification a second. Oh, Callan, yes.
Yeah, so just you had like a script there, like LMOTS or whatever in BitAuth IDE. That's the actual algorithm for signing and verifying, or like that's in the contract somewhere.
Yes. Oh yeah. Let's look at that real quick. Because hopefully earlier you got a sense for how Lamport signatures work and then how Internet signatures work. It's quite simple.
It seems computationally intensive, or am I wrong? It's not.
It
fits in the contract.
It is computationally intensive if you're looking at it in isolation. But if you divide it out over the cost of the signature, over the size of the signature, it's not. It's well within our existing limits. It's well within already the current worst case. Rather, it's well within what the worst case was before 2025. The VM limits upgrade this year brought the worst case down. It made the worst case safer. And of course, it's within that new lower safer worst case, right? So yes, what matters is knowing that the signatures are very large, 2.6 kilobytes for the whole overhead and everything when you do the actual quantum bit. But there again, it's really nice that our contract system is capable enough to not need to have that on chain right now, or have an upgrade specifically for quantum security. It's possible there, just as we have it. Unrolling the loops, it would be quite a bit of a mess. You'll see we use functions in a few different ways too, and there's a few places where here we have a function that's specifically used to make something work as required for the RFC, which if we were going to have our quantum version that is not exactly RFC compliant, we could save some of these bytes. But it seems these bytes are unlikely to even hit the chain for the next 5 to 10 years in a lot of ways. So it's possible that in 5 years we'll have a quantum adversary, and then these bytes would hit the chain. But it certainly is not worth having our own standard to save a couple bytes for something that might not happen. And you'll see there's a few places where we talk about RFC 8554 compatibility. But what it's doing is looping through and performing it gets the it's even. The code is something probably to review on your own, because you kind of need to look over here and then watch what's happening in the evaluation if you're working with the assembly, of course. But I will leave it up here so you can see so you can read this as I'm talking. What's happening under the covers? You hash the wallet is going to hash the the signing serialization, and it uses the same signing serialization that is present on chain. It actually uses it on the wallet side. The internal evaluation, introspections inside the internal evaluations. This is not on the live ide.bitauth.com, so it's just worked around in the IDE right now. But introspections inside internal evaluations actually look outside to what has been produced already during the compilation in the wallet. So there is like when the wallet is creating the transaction, there would be a circular, reference there if it didn't know what it needed already in the spots that it needed. So maybe read the comments on it. But the short answer is that the wallet is, at the time of signing, looking at the transaction that it's going to sign using the cache assembly. It's reading the cache assembly and doing the introspection on the transaction it's about to sign, produces the signing serialization it needs to sign, and then it runs the LMOTS sign script, which doesn't actually happen on chain. The script is just run in your wallet to perform the signature and produce the final signature. And it does all of that as part of generating the unlocking bytecode for the quantum lock. So quantum unlock, if you look up here, quantum signature is inside. Here, I hovered it. Quantum signature is inside the internal evaluation. And if I hover it, you'll see it's a big old signature that it's sticking in right there. And then quantum key identifier is part of the RFC. 0 is we always use for privacy. There's a message randomizer is an important thing, and we use it properly. And then the quantum sign message. This is the result of is the concatenation of the serialization of the whole transaction and of the script we want it to run to verify that there has been no malleation in the mempool. And again, pushing it here means that we can, from the wallet's perspective, just upgrade some wallet code rather than moving something on the chain when we need to upgrade, if we need to upgrade how the signing serialization works. And this is especially actually a good contextual thing, is that if you're using a hardware wallet, SIG-hash UTXOs is really critical. And if you're not, if you're using a full node, then you might not care because you can already see what the UTXOs are yourself. Really trivially, you're not like passing this message to a more secure environment. And so you might have two different ways of spending. One is a SIG-hash all simple thing, and then one is costs 10 more bytes to do SIG-hash UTXOs to embed it in there. And you can save those 10 bytes by not using that one. You can use the SIG-hash all if you're using a full node. So if that makes sense. So being able to just have the wallet choose at signing time which code it wants to use, and it can have multiple different signing paths, obviously, just right in here, means that those bytes, having the wallet being able to choose that at signing time means that those bytes never hit the chain in the same way as it's useful for the Quantumroot construction too. All right.
Dumb question. So, and you said this earlier. So the key that you're using to sign is, like you said, some hash magic stuff, but it's derived from a private key somehow, right? The public key. So the key you're using to sign is, let's look at it. Quantum signature is down here, template quantum signature. Quantum private key, there's the quantum private key. So let's go look at that. Quantum private key starts with, so this is all an internal evaluation. This is just like using it as a template. Starts with the LMOTS key identifier. Look at that real quick. Oh, and that's a, let's see, LMOTS key identifier. There it is. So it starts from identifier source public key. So it's a key path in the wallet. We can click up here. Identifier source. There we are. So hardened derivation. It is one of the hardened derivations that the wallet would assign its own unique key path for. So you start there and you
take this is all in order to support the RFC. Like we don't even need those things in our specific case, depending on some of your assumptions, but much safer in general to just follow the RFC exactly. And then quantum private key source, you see that comes from yet another source, and it's the public key of what is a hardened private key. So from a quantum perspective, it's different by a hash, and so it's safe in its distance from all of the other places, but it's still derived from the same HD private key. And then you'll see LM-OTS private key. The way we produce a private key, this is the heaviest thing you can do, and it's this heavy loop. It runs it 66 times. And produces, here we're running it against a test vector, produces a known correct private key, and they're equal, right? But it's doing, yeah, I'd forgotten. So it's this loop runs 66 times. It's doing a lot of reintegrating its previous result, sticking it in the pre-image for the next thing and hashing that again, and reintegrating the previous result and hashing that again. And that's to stop attacks where you can simultaneously try to attack all of the hashes in the system. And it's just a theoretical weakener, really, in our case. But Winternet schemes after like 2013 started doing this this XORing previous information in order to thwart that attack. And that's part of the RFC and then part of the NIST standard. So it's doing that correctly. And it does it in cache assembly so that no wallet will ever have to do it correctly. And the test vectors are there. And then it's doing all of that to produce the private key that it then uses to produce the public key. Oh yeah, so it's 66 across and then 15 down. I'm sorry, I was just drawing a blank. Where's the public key? There's a public key derivation. Public key derivation. What did I do? Oh, I was just showing you public. Yes, okay, 66 across. Yes. So public key derivation. Did I show you private? Yes, I was just showing you private. Great. And you can see here I was being lazy instead of optimizing really well. Yes, public key derivation is very similar to something that already very similar to derived key. This is the verification function, and so it's optimized. But public key derivation again is another thing that only happens in the wallet. But it's fortunately for hash-based signing systems, public key derivation is the same. Is very, very similar to the signature validation check, because when I give you a signature, I'm giving you parts of my public key that have been hashed to various levels along the chain. And then in order to check it, you go and hash each one of those the correct amount of times to get it all the way down to what is the public key. Then you hash that all together and check that it was in the contract. So yes, those private key derivation from a simple HD BIP32 HD key is shown here, and then public derivation from that is happening in cache assembly, and then a signature from that is also happening in cache assembly. And then the only thing of this stuff that shows up on chain is the very optimized derived key candidate function, which actually does those things starting from the right spots in the graph, does it on chain and checks that it's equal. Did I explain that reasonably?
Yeah. And just to underscore, like, so the advantage, so one trivial, like, naive thing you can do is not even care about hashing and quantum resistance. Just have some public key you never reveal and some span path, right? But that, like, as soon as you have Q day, that's like instantly exploitable by quantum computers. Whereas with this system, you reveal, you can do a few signings with the same key before it becomes attackable. Am I understanding that correctly?
The key you're talking about, you were talking about at first, I think, an elliptic curve key.
Yeah, sorry, an elliptic curve key, just a plain elliptic curve. Like forget about all this hashing stuff. Just have a plain hidden elliptic curve key that no one knows about that you can sign with, right? But the problem with that is that if you have quantum Q day, it becomes instantly exploitable by quantum computers.
Yeah,
so you have to be very sure you only signed once with it. Whereas with this,
it's a worthwhile distinction.
Times, or is that what the advantage is? Or
I think it is a worthwhile distinction to still distinguish between like P2PKH is reasonably quantum secure and can be upgraded to be quantum secure, whereas P2PK without the hash, like pay to public key that's unhashed, cannot be upgraded to be quantum secure. A quantum attacker will sweep all of those at the same time, almost certainly, and they'll try to do it across multiple chains. They'll probably try to drip it out initially, and then once people start to get the hint that there is a real possibility of a quantum attacker, they'll just take the rest of everything else that they can see over long-term attack horizons. Whereas it seems very plausible still that a quantum attacker will not be able to attack in the mempool on day one. And so the very old discussion of is P2PKH wiser than P2PK because of the quantum security, I think that's still quite relevant. And at the very least, because it is possible to safely upgrade P2PKH to switch from accepting signatures, or even to probably initially to accept both, and then eventually for a network to turn off the elliptic curve signing option. But it's perfectly possible for you to start with a hash of for your public key to be a hash. I'm sorry, for the public element to be a hash of a public key, and then for you to produce a zero knowledge proof or use a commitment scheme to prove that you knew the pre-image of the hash, which was your public key, before
before it can be
in a way that a quantum attacker can't reverse into a private key and steal the money, right? There are still some issues with P2PKH in that the hash is too short. It's 20 bytes, and so it does become attackable with right 20. Yes, it's 20. Hash 160. It becomes attackable with Grover's algorithm, but there is a big window between cryptographically relevant quantum computers breaking EC crypto and then being able to muster enough to apply Grover's algorithm to hashes in a meaningful way. Like there's a big compute difference. So like Q-Day, they're going to steal all the elliptic curve crypto, but hash protected crypto, even if the hashes are too short, those will probably be protected for a little while, we think. That at least seems to be expert consensus, and I have no more expertise on that than you'll find more information from other people more expert on that topic. But yeah, there is a gap between elliptic curve being keys being broken and people being able to reverse even a 20 byte hash. But 32 byte hashes are very widely considered to be safe for decades to come, until we have a very different model of physics or this math. All right. Well, thank you all very much for hopping on, and I'll cut it here so that the video doesn't get too much longer. I'm very happy to take other questions on X.com or Bitcoin Cash Research or wherever, and would appreciate deep reviews if anyone listening is willing. I'd appreciate if you find places to shave off some bytes, curious strategies to make things more efficient, and then of course if you find any weird attacks that aren't addressed already, those would be great to know about as well. And thank you very much.
Thanks, Jason.
Thank you.
Thank you, Jason. Thank you very much.
Hi guys.
Thank you.
Cheers.
Bye-bye.
All right, stop to the stream. Welcome to hang on to if you want.
I think I understood like the 16%